Hello everyone, thanks for coming, and we're happy to have Xiaocan here to give us a seminar talk. Xiaocan is a research scientist working at Dartmouth College, and he got his PhD from University of Alabama in Huntsville in 2016, and then he did his postdoc at Los Alamos National Laboratory, and then he went to Dartmouth just before the pandemic. His research focuses on high-energy processes in space and solar physics using numerical simulations and derivative analysis. And today, he's going to tell us about his recent progress in modeling particle acceleration and transport during solar flares. And I think this will be something with some fantastic and fancy images that he will show us.
Okay, thanks, Pete, for the introduction. And I appreciate this opportunity and the invitation to speak with you all today. As we mentioned, I will present our recent progress in modeling particle acceleration and transport during solar flares. And I will present some results in small scales about particle acceleration and transport, and also the particle acceleration and transport at large scales, like large scale solar flares. And I will explain why we have to do both in our framework. I want to thank my collaborators first. They contribute to different parts of this project. We come from different institutions, and working together, we have built a comprehensive framework to study particle acceleration and transport in solar flares and beyond. And the framework means the collaboration is still growing. For example, Ben and I are trying to find opportunities to collaborate on the SEP acceleration. For example, we want to say whether the flare accelerated particles can contribute to the seed population for the SEP acceleration. So my presentation will have 4 parts. In the first part, I will give some introduction on the background that's relevant to the discussion. And then I will introduce the particle acceleration in solar flares, and the challenges in modeling them, modeling the problem, and the framework we are building to address the challenges. In the second part, I will present the results in kinetic modeling of particle acceleration. I will focus on the particle acceleration mechanisms in a small-scale reflection layer and the formation of polar energy spectrum in a 3D reflection layer. So I will explain how these two physics contribute to the particle acceleration at large scales. And moving to the third part, I will present our results in modeling large-scale acceleration and transport in solar flares. I will show some results on the particle acceleration in the large-scale flare reflection region, in the flare condition shock region, and the 3D flare region. And I think for this group, you may be more interested in the SEP acceleration. I will show some progress on how the particle get released from the flare region, and probably can contribute to the seed population for the CME acceleration. Lastly, I will summarize the takeaways of my presentation. So let's dive into the first part of my presentation. So solar flares can release a large amount of magnetic energy stored in the solar corona, and the converted magnetic energy can be used to heat the plasma to tens of million degrees or accelerate particles to very high energies. These accelerated particles can generate the non-thermal emissions at different energy bands. For example, the hard X-ray emission produced by non-thermal electrons, the gamma ray emission produced by non-thermal ions, and some of the small part of the flare accelerated particles can propagate out of the flare region and become the so-called impulsive SEP events. So for most of the flare accelerated particles, the non-thermal emission is critical to diagnose their properties. And since the recent era, our understanding of flare acceleration has been significantly advanced. So from the emission observation, we know that electrons can be accelerated to a few MeV, and ounce up to GeV. And then for the photon spectrum, usually, especially the hot X-ray photon spectrum, it usually has a power law shape, which can be generated by the power law electron of double power law electron distributions. And the emission image often showing that most of the emissions come from the flare foot point. But however, it does not mean that the particles are accelerated at the flare foot points. So they are most likely accelerated elsewhere and then transported to the foot points and produce the observed emissions. So the broad question is how these particles accelerate in solar flares. And there are, of course, many possible acceleration mechanisms, and but the recent observations, more and more observations showing that the flare recollection site is critical in particle acceleration. And one of the key observational evidence is about the flare loop hot X-ray emission. So this indicates that the flare accelerated electrons are probably originated above the flare loops and close to the flare recollection site. And more direct evidence of the flare recollection acceleration comes from the radio observation. For example, using the Janskin VLA observation, Bin-Chen et al. Show multiple electron beams originated from this very compact region, likely to be the recollection site in solar flare. And recently, the YALSA observations show that the microwave emission can fill the entire flare recollection site, suggesting that the electron acceleration in flare recollection region is quite efficient. So to get our understanding of the particle acceleration in solar flares, we usually use so-called standard flare CMB model. Here's one example from Ning and Forbes. And in the standard model, the magnetic energy release is thought to occur above the flare loops and due to the reconnection in this elongated current sheet behind this ejected flux loop. And the flare event here is the September 10th, 2017 flare. It's an outstanding example of the standard flare model. So the observations show resemblance between the hollow structure and the ejected flux loop in the model. So we can see that in the standard model, the recollection plays a central role, and that's why it is one of the acceleration mechanisms in solar flares. So besides recollection, there's also a lot of other proposed mechanisms that can explain some of the aspects of the flare acceleration, including, for example, the recollection-driven termination shocks near the flare loop top, and the plasma turbulence driven by recollection outflow, large-scale waves in these flare loops, and also magnetic traps. So all these mechanisms is possible to explain some of the observations, but we know that the recollection plays a central role in solar flares. That's why we want to understand how particles are accelerated in magnetic recollection region. So for those are not familiar with recollection, so it's a fundamental plasma process that can reorganize the magnetic topology. So it will break the field lines and reconnect it at a small region called the diffusion region. And so it can convert the magnetic energy into the plasma kinetic energy, and the converted energy can be used to heat the plasma and also accelerate non-thermal particles. So because the field line has to be broken and reconnected in this small region, the small-scale kinetic physics is critical for understanding reconnection and associated particle energization.
I have a question here. You mentioned accelerating. I don't know about this, but you mentioned accelerating non-thermal particles, one-off thermal particles with the connection.
Yes. During reconnection, the converted energy can also be used to heat the plasma. That's the thermal particle emission. And depending on the plasma parameters, I think in some of the regions, most of the converted energy will go to the heating, and a small part will go to non-small acceleration. But in some case, like the low galaxy or low beta case, the non-thermal acceleration can be as efficient as the heating, and even takes more energy than the heating. Yeah. So as mentioned, the small scale kinetic physics is critical. But meanwhile, if we want to understand the large scale particle acceleration in solar flares, we need to capture the flare geometry and dynamics. And we can see from this diagram that there's about 8 orders of magnitude separation between the kinetic scales and the solar eruption. That's why it's very challenging to model particle acceleration in solar flares. And therefore we needed to do modeling studies at both scales, kinetic scale and the large scales. And we hope that the studies at different scales can talk to each other at some medium scales, for example, the MHD grid scale. So that's basically our approach. So we have built this framework to address this challenge. And in this framework, we use kinetic modeling and transport theories to study the particle acceleration and the mechanisms and the turbulence properties, particle scattering and transport. And this provides the foundation for the large-scale models that couples MHD simulations and the macroscopic particle model. And this kind of model is capable of providing particle distributions can vary spatially or temporally. And these particle distributions can be compared with those derived from emission observations, such as RASI, YOPSA. And also, if the particles manage to propagate out of the flare region, then it can be compared with the particle solar probe or solar orbiter observations. And these particle distributions can also be used to do emission modeling, for example, to generate the emission maps at the hard X-ray bands or the microwave emission band. And then it can be compared directly with the emission observations from different observation perspectives. And here is a more detailed diagram. There's a lot of components here. I won't go to all the details. And basically, we have observation components. We have several modeling components, and the different components are interlinked with different physics quantities and physics processes. And for the rest of the talk, I will present some results in the kinetic simulations to study the particle acceleration mechanism and the formation of polar spectrum in reconnection. And I will show some results using so-called global particle acceleration transport model, GPAD model. And this model will provide the energetic particle distribution varying spatially and temporally. And we will do some comparison between the modeling results with simulations to demonstrate that the model can explain some of the aspects of the observation in solar flares. So that leads us to the second part of this talk. And before I go to the second part, do you have any comments, questions so far? No? Okay. So let's dive into the second part. So I will show some kinetic modeling of results of particle acceleration. So historically, it's thought that particles can only be accelerated near the reconnection X point. For example, maybe for this case, the reconnection X point is somewhere here. But in the past 2 decades, more and more studies have demonstrated that the Fermi mechanism is critical for reconnection to accelerate a large number of particles. Because the filling factor of the so-called reconnection X line is typically very small in large-scale systems such as solar flares. And for example, the most famous study is Dimitri et al. In 2006. And also, these studies have shown that the elongated current sheet will break into multiple so-called magnetic islands or plasmoids. And this is critical because then the particles can be energized by the Fermi mechanism at multiple locations. For example, in contracting magnetic islands or in island merging regions. So that's why the particles can getting higher and higher energy in a large scale reconnection layer when they interact with different magnetic structures.
Just to be sure, like the green line would be. So what are exactly the blue and the green line?
Oh, sorry, I didn't go to the detail. So the blue lines are the magnetic field lines. So it's a diagram. The green line is supposed to be the trajectory of the particle, but it's not actually. There's no gyro motion. Just show that.
Yeah. But like you can have some like way like in the bottom one's actually kind of surprising. Like this way and that, as if it was bouncing on the slide.
Yeah. This one, right? Yeah.
Exactly.
This one, for example, if we have some fluctuations in this outflow region, the particles can be scattered back to this exhaust and then get energy again.
Does it mean that the field lines moving at happening speed,
right?
As you showed here,
yes.
And the particles moving here and then gain more energy because due to interaction with
due to interaction with the outflow.
Yeah.
Okay. In the past decade, a lot of studies have been dedicated to quantify these different mechanisms, and so the results, I think the I show you two key results here. The first one is that the simulation shown that the Fermi mechanism in reconnection layer is associated with the so-called particle curvature drift, and it dominates the high energy particle acceleration. What I mean the acceleration associated with curvature drift. Here the equation is the energy gain rate associated with particle curvature drift we see. So we can rewrite it in this expression where the VE is the equal speed drift velocity and the kappa is magnetic curvature. So in reconnection, as shown here, the reconnection outflow is driven by the tension force on the magnetic field lines, the curved field lines. So that's why the reconnection outflow is aligned with the magnetic curvature direction. So that's why the VE dot kappa is positive. That's how the particle can get energy in the reconnection layer. And interestingly, we can also notice that the energy gain rate is proportional to particle parallel kinetic energy. That means that when we calculate the so-called acceleration rate, we divide the particle energization rate by the particle energy. We probably get roughly a constant. And that's indeed the case as shown here. This is the energy-dependent particle acceleration rate for different mechanisms, such as those associated with curvature drift, the gradient drift, the parallel electric field. So you can see the dominant mechanism is the Fermi mechanism associated with curvature drift, and the rate due to this mechanism is roughly a constant for energy particles. So the narrative finding of this kinetic simulation is that the Fermi mechanism tends to be surprised when there's a gap field. So the gap field is a magnetic field component perpendicular to the reconnection plane. So when you can imagine that when there's a gap field, the field lines in the curved field lines will become more straight. You can imagine if the gap field is infinity, the field line will become straight. So that means the magnetic curvature will become smaller. So that's why the acceleration will become slower in this by this mechanism. So there's of course a lot of other studies on the particle acceleration in the small scale reconnection layer, but I think these two are quite critical for understanding particle acceleration at large scales. And I think we have learned a lot from these simulations. But probably here I will switch to a little bit different topic. So even though we have learned a lot about the particle accelerating mechanism, there's one critical feature of the reflection accelerated particles, which is the formation of power law energy spectrum. Was not resolved until recently. So the power law energy spectrum are commonly observed in space plasmas near reflection sites. For example, in Earth's magnetic tail, the electron power law distribution have been seen near the reflection diffusion region in the Earth's magnetic tail. And although there's no in situ observation in solar flares, we do have the photon spectrum, and which often show the power law tail at high energies. As I mentioned previously, these power law tails can be generated by power law electron or double power law electron distributions. So that's why the power law spectrum is a common feature in the reflection accelerated particles. That's why we need to obtain this kind of feature in modeling and simulation of magnetic reflection. But it turned out to be quite difficult for a lot of years. And I think, so eventually what we found is that the challenge is actually partly due to the simulation setup, because most of the simulation we have performed are in 2D geometry because cheaper. And and for the 2D simulation, the high energy particles tend to be trapped in the local magnetic structure, such as magnetic island. So here is one example of our 2D simulation. The top panel is the high energy electron distribution. We can see that most of the high energy electrons are in these magnetic islands. And the corresponding bottom panel is the acceleration rate. So which, I mean, due to the Fermi mechanism, and the regions colored in red means that a particle can be rapidly accelerated. So we can see from this, compare these two panels, we can see that once the particles get trapped in this island, they cannot access this red region. That's why the acceleration becomes slower and slower as the simulation proceeds. And eventually it prevents the 2D simulation to produce a robust power law formation.
May I know why 2D simulation will trap particles, and then 3D does not trap particles?
Yeah, 2D is how to say that? So in the 2D, the magnetic field lines is like closed circles. So once particle get into there, that's difficult for them to get out. I think the only possibility the particle can get out is when they collide with another structure, the particle can be energized again. But if there's the isolated island, mathematically, the particle will just move around this closed field lines forever. I mean, the diffusion, that's a small diffusion, but this diffusion is typically not enough for the particle to get.
So in 3 dimensions, do those circles turn into helixes?
Yeah, in 3D, I will show the later in 2 slides. So you can see that in 3D, the field line is completely chaotic, and then the particles cannot be trapped in the local structure.
Right.
Those magnetic, if you're interested about the adapter, I'm going to use my question for you. So,
That's good. What's your question?
just like, what does the magnetic island look like in 3D?
Oh,
Like, what's the equivalent? Because magnetic island is basically the result of the connection that we found them. What's the result in 3D? That you should talk about adapter as well.
yeah, I will basically first just shown here. Here is the flux rope. So, I mean, this is the island in 3D.
Yeah.
So it's an elongated structure initially, but if we, I didn't include moving here. Let me see if I can find the movie. That's quick enough. Okay, let's see, where's the movie? I can't find the movie. Yeah, anyway, we can talk afterwards.
Or
Yeah, I cannot locate where the movie is. But the basic part is that the flux group will become unstable and then will break apart, and that's why the particle cannot stay forever in this flux group. So as I mentioned, the 2D particles are artificially trapped in the 2D simulation. That's why we need a 3D simulation. So we did some of the 3D simulation actually a few years ago before the pandemic. And these simulations are quite massive, and it takes a lot of effort to do analysis. And we have to do in situ diagnostics and analysis to analyze the massive simulation data. And here I put a link of the simulation decks and also the method to compare and run the code on different platforms. I don't know if any of you guys are interested in this kind of simulation, you can try it out if you are doing similar things. Because I think the code we use is actually quite efficient for this kind of work. So what we found in the 3D simulation here is one example is from one of the 3D simulation at a relatively low galaxy field is 0.2. We can say that electron distribution can develop into a polar tail, which is like still roughly only one order of magnitude extension. So even with this massive 3D simulation, it's still quite difficult, but it seems quite robust. And it's the maximum energy of the particle distribution keep evolving. And the spectrum slope -4 actually is quite close to those observed in solar flares and the Earth's magnetic tail, especially the Earth's magnetic tail, where the galaxy field is low. And the embedded plot here compares the spectrum in 2D and 3D simulation. The 3D are in the solid line, 2D dotted line. So you can see, of course, the electrons are shared to higher energy in the 3D simulation. And more importantly, the maximum energy just keep increasing as the reflection proceeds. However, in contrast, in the 2D simulation, we see that the maximum energy does not change much after some time. And the particle flux just keep panning out at a lower energy. That's why the spectrum will become steeper and steeper as the simulation evolves. That's why it's difficult to obtain a stable polar distribution in a 2D simulation. But what makes the difference between 2D and 3D? So what we found that two aspects of the 3D physics are critical. The first one is that the field line becomes chaotic, as I mentioned before. So the top panel here plot the turbulent reflection layer overplotted about 20 magnetic field lines. So the field lines are initially very close to each other. I mean, we start tracing them very close to each other. You can see these field lines quickly diverge from each other, and within one crossing through the system, they can access a very broad region in the reflection layer. So you can imagine particles following these field lines will have access to multiple accelerating regions and get more energies. So another aspect of the 3D physics is the self-generated turbulence in the 3D reflection layer. Here I plot some magnetic power spectrum. But the self-generated turbulence has been studied for over a decade, and we expected that the self-generated turbulence can scatter the particles, so they won't be trapped in the local structures. I mean, at least preventing them to be trapped forever in some local structures. So this will also help the particle transporter, so the particle can access multiple accelerating regions and getting higher and higher energy. To illustrate this fast transport of these energy particles, we did some test particle simulations using the pig fields as background. Here, shows the reflection layer overplotted with some field lines in green color. And initially we inject particles in this large flux loop, and they are very close to each other, right? And we can see that. So after a short time, they can fill the entire flare, not flare, entire reflection region. And if it is 2D simulation, we expect this particle will stay in this large scale flux loop forever. So because of the fast particle transport, they can access these red regions. It's similar as the ones showed before for the 2D simulation. So now the high energy particle can access these red regions. That's why they can have a more efficient acceleration. So as discussed previously, the particle energy gain rate due to the Fermi mechanism is proportional to particle parallel kinetic energy, and the section rate defined here is going to be roughly constant. We have seen this figure before. Yes, it is roughly constant for high energy particles, although it's not perfect. But I think here I want to show this red figure. It compares the rate for the between the 2D and 3D simulation. The 3D simulation are in the blue colors, the 2D are in the orange colors. The dollar and dash line are the two time frames. So we can see that the section rate is roughly constant for the high energy particle in the 3D simulation, but it is strongly fluctuate in the 2D simulation and even become negative in the 2D simulation. So we can imagine that such unstable section rate will make the part of emission quite difficult in the 2D simulation.
Sorry for a question. Here your gradient drift will prohibit the acceleration because it contributes to negative acceleration rate. Can it be positive?
Yeah, here I only show the very high energy tail. Yeah. In some low energy part, probably it can be over, can be positive. Yeah. But you can imagine that in general, in reconnection, the field, the magnetic field is dissipated, right? So the field will become weaker. So in general, the gradient drift or the battle transfer will give like a left cooling effects because of weakening field. So what is the time now? So how much time do I have? Like 15 minutes. Okay, then that would be. So let's give a short summary of this part of the work. So I think the 2 points I want to emphasize that the first is the high energy particle acceleration is primarily due to the Fermi mechanism. And secondly, that I will show the self-generated turbulence and also chaotic field lines will lead to efficient particle scattering and transport. And particle acceleration consequently is the report of formation in the 3D reflection layer. So this is the 2 key points. With these 2 key physics, we can then attempt to study particle acceleration at large scales. So I will show that why is that. So that leads on to the third part of this presentation. So although we have some fantastic results in the very small scale simulations, we can see from this diagram that even the largest peak simulation is still smaller than the finest MHD grade. So there's no hope that we can simulate the whole reflection set using just a single large-scale simulation. So that's why it's still challenging to model the large-scale particle acceleration and transport. And however, it has never been a better time to work on particle acceleration and transport in solar flare because of this significant progress in the past few years in observations and also MHD simulations. So in observations, the ground-based radio observations by YOSA and hosted at NGIT New Jersey Institute of Technology, showed excellent capabilities in reviewing the spatially dependent electron distributions and also magnetic field profile. Meanwhile, the state-of-the-art MHD simulations can provide accurate plasma and magnetic field profiles matching the observations. So they have a, I think, publication on Nature Astronomy for 2020. So however, the MHD simulation cannot provide the non-thermal particles. So we need to couple the MHD simulations with some kind of particle model. Then we can explain the non-thermal particle generation and the non-thermal emission in solar flares. So for the macroscopic particle model, there are different kind of particle models. And I think the ones with the longest history is so-called single dome models. So this kind of model can quickly generate the observables of the whole flare and or one region, for example, in the flare rooftops or in the recurrent exhaust. But this kind of model cannot incorporate the flare geometry and dynamics, so it is intrinsically incompatible with the modern spectroscopy observations. So the more promising ones are those that can be coupled with MHD simulations. For example, the test particle simulation has been widely used. And you can either evolve the full particle orbit or the Gaussian center orbits. But this kind of model has low subgrid physics to scatter the particles, for example. It also has low feedback to the background fields. And often the model gives much harder spectra than those observed in solar flares. And also there are drift kinetic model, and actually the drift kinetic is quite similar to the test particle simulations involving the Gaussian center orbits. And it has low feedback. But there are some recent progress done by University of Maryland by Jim Drake and his students, Harvey Arnold. So they show that it's possible to include the feedback in the drift kinetic model, and then their so-called kit global model can produce very long power law distributions. And for our framework, we primarily use the transport models. We can either solve the Fox transport equation or the Parker transport equation in our model. So the two key physics mentioned in the second part of this talk, firstly the particle scattering and also the Fermi mechanism, are often already built into this transport equation. For example, in the Parker transport equation, these two blue terms highlights the effect due to the scattering and also the acceleration due to the Fermi mechanism. So according to the transport theory, the particle distribution then can be determined by the MHD fields and also the turbulence properties. And the model will provide spatially and temporally dependent particle distributions. So we have used this model to study particle acceleration and transport in local recurrent layers. And the local recurrent layer means that the recurrent layer is periodic along the optical directions. It does not interact with the ambient plasma. And we show that the particle energy spectrum for electrons and protons can change with the gas field strength and plasma beta. So for example, when we increase the gas field from 0 to 1, the spectrum will become deeper and also the maximum energy will become smaller. And also similarly, when we increase the plasma beta from 1% to 1, the spectrum also becomes deeper. So in a low gas field and low beta case, electrons can be accelerated to MeV, and the protons can be accelerated to tens of MeV or higher. The bottom figure here basically shows that the model can generate the particle maps. And we can imagine that we can use this kind of map to produce non-thermal emissions. So of course, we know that the reconnection in solar flares is not isolated. It is part of the much larger system. That's why we have been using this model to study particle acceleration in a more realistic geometry. So in this work, we studied the electron acceleration in the early impulsive phase of the 2017 September 10th flare. So we use the MHD simulation setup adapted from the simulation deck developed by Chen Tyson for Chen et al. 2020 Nature Astronomy. And the model started from this Forbes mean model. Here, the figure shows the evolution of the system. You can see the ejection of flux loop and also the formation of large-scale current sheet. And when solving the particle trans model, we can show that the electron can be accelerated to a few hundred keV or even MeV. And here we have seen this plot before. It shows that the microwave emission can fill the flare reflection region. This middle two panels shows the electron distribution at the two energy bands. So you can see the kind of electron can fill the flare reflection region, which is consistent with what are indicated by the observations. The red panel compares the model generated spectrum and also those derived from emission observations shown in black lines. So you can see the model can reproduce the general spectrum feature of the observations. I probably don't have enough time for the actual scale here. This slide. For this basically shows that we can also use this model to study the acceleration near the termination shocks at the flare loop tops. This is a set of work done by my collaborator Xiaocan et al. And here the red panels are showing the synthetic hot X-ray emission. Especially you can look at these two panels. So you can see the hot X-ray emission can reproduce both the loop top source and also the full point source. And also the simulation can also be used to generate these multi-frequency microwave emissions. So these are also consistent with what are observed by the Xiaocan mission. So this set of works demonstrated the capability of this model, but the modeling effort does not stop there. We have recently extended the model to 3D. Here, is a 3D MHD simulation done by Chen Tyson et al. And it's published last year on Nature Astronomy. So this 3D simulation has all kinds of possible particle acceleration mechanisms, including the flare reflection current sheet, the termination shocks, and the turbulent shock downstream, including the so-called finger-like structure. It's the superarcade downflows. And we solved the model in the 3D MHD simulations, and the basic conclusion is that the different mechanisms can work together to separate a large number of electrons over MeV. And the plot here is just average along the outflow direction, the autoplane direction, and at the three different energy bands compared with what we have seen in the 2D simulation. Let me quickly jump back. This is a map of the 2D simulation. The 3D particle distribution are more diffused at the loop top region. And more importantly, we see that the energy particles peak at the loop tops instead of in the current sheet or when the ions collide. So this kind of feature is more consistent with observations. That's why the 3D is quite important to explain the observations. And also because it's 3D, we can look the particle distribution from different perspectives. Here is a 2D slice through the center of the current sheet. So we can see a lot of structures, and also again, we can see the flux peak in the loop top region. If I can play a movie, I show the dynamic evolution of the system. What is the time now? I still. Yeah, you basically say, yeah, okay, the 3D is quite complicated, but has a lot of structures. Okay, this is last part of my presentation. Is I think I don't know you guys what you guys are working on, but I think it's going to be more interesting to this working on SCP acceleration. So you may wonder how this flare acceleration particle contribute to the SCP acceleration or the space weather effects. And we have some ongoing project to study how these particles get released from the flare region. And in our model, we anticipated that the flare accelerated particles get released along the open field lines, which is going to be facilitated by the interchange reconnection, and then propagate to the CME front region and become an important seed population for the SEP acceleration by CME-driven shocks. So we did some modeling studies. Here we solve the Fox transport equation with ARMS MHD simulation results. The MHD simulation is done by Hugh Darlene at the University of Maryland. So this is a simulation up to 5 solar radii, and the flares is very close to a very small region here. So we inject the particles in the flare region, and we can see that the flare accelerated particle cannot be confined in the flare region. They can quickly propagate out due to this interchange reconnection between the injected flux loop and the open field lines. And the particle can spread over 90 degrees. And here is not longitudinal. It's like additive. Okay, that's basically all my presentation. Here is the summary of the takeaways. I will leave it here. You guys will have more questions, comments. Time for that. Thank you.
Are there any questions about in person?
Yeah, in the video you just showed, there seems to be a very slight difference in the timing of the extension. What is the video?
You mean which video? This one?
There just seems to be like a delay in what is the difference between the between these? It's called like ever so slight difference in timing and expansion.
That's because of different energy, right?
This is a different energy of the particle. So for energy particles, it has going to be have a faster propagation. Yeah, I think.
Let's say lower energy comes up earlier compared to
Right, but before the high energy particles can expand, they have to be accelerated to that high energy.
yeah.
Mhm.
That's why.
So, and that's the density of polygon that you see here, like what's the color?
Yeah, this is
And
the
density.
density of
Density, okay.
But I haven't really checked the calculate it is that density of flux. What is that?
There's some quantity of particle
Yeah.
that is given in energy.
Action, so then which implies density.
Right.
Where do you see the end?
Yeah,
Because there's 10 and
it's not labeling each one of these.
So I think that's for modelers we are not quite accurate at the quantities. Usually we have density, but we mean flux means density.
Okay.
Kind of confusing.
Oh, okay.
But as we mentioned that when we trying to work with observers like this one to compare with initial observation, we have to be quite accurate to define the same quantity.
Yeah, of course.
think you mentioned that the acceleration is important when there's guide field. And I think there are many people at UNH are doing random sphere study.
Mhm.
And then how do you think about something with, because you also mentioned something with acceleration and connection in mechanical details. So is this guide field important in mechanical details or not? If not, then the low plasma beta will contribute to the acceleration.
So any of you working on that? No. So I expect maybe someone from UH will be here, but she's not. So in the material, most cases low gas field rejection.
Yes, okay.
Gas field, but we also studied the micro pulse, where the gas field can be a broader range, can be low gas field or high gas field. And actually have some ongoing collaboration with Kevin and his student Steven here. Kevin Janice, right? On the material reconnection.
Something raising question on mine, but maybe you should show us the video. You managed to find like I am actors, like I like videos.
See if I can find it somewhere.
Yeah, if a picture paints 1,000 words, then a movie paints 1,000 pictures.
Yeah. To the thousands, you know, like the power of thousand.
So this is the simulation.
Oh.
So you can see this structure got destroyed and they propagate. And the layer become quite turbulent.
So you can, like you reach just about to like field collapsing, like that's initial, like, and you have some speed of the magnetic fields, some speed and magnetic doing that way, and then all the rest is like, okay, that's interesting.
Yeah, you can see the whole layer become like. I mean, these lines are the sample field lines. They become spaghetti like.
That's really interesting. And beautiful. Thank you, man. So let's expand out the area. Thank you everyone for coming, and this week is June with Rise of One. We have another signal which will be about mission concept called scope. So same time as usual, but this time per day.